And we're looking forward to working with more partners to enable this transition for development, for algorithm, and also for business. 接下来让我们有请来自中兴公司的韩炳涛先生分享如何基于星云大模型助力企业研发效率提升。Now I would like to invite Mr. Han Bingtao, Chief AI Scientist of ZTE, to share how to help enterprises to improve rotated efficiency based on Nebula Large Language Model. 有请。
Thanks very much for the invitation. I'm pleased to introduce BebulaLLMs, a series of new large language models developed by ZTE. Today, many outstanding companies are undergoing digital transformation to become smart enterprises, which make us constantly think about the role the large model can play in this evolution. After carefully investigating, we decided to develop BebulaLLMs. I would like to describe BebulaLLM with the formula 1 plus x plus n. 1 represents the base models. By leveraging both public available data and the ZTE's in-house high-quality data, we have enough confidence for the model's efficiency and the data security. This ensures that the model is primed for commercial applications. N stands for the professional domains where the LLM is applied. From our perspective, we categorize these into 3 segments. Firstly, the RnD domain, where we have pioneered the Nebula RnD LLM. This tool is designed to enhance R&D productivity and has already demonstrated significant success. Currently, Nebula RnD LLM are leading in the industry in terms of programming capability. The second category is the telecom field. We have developed Nebula Telecom LLM, highly integrating this model with autonomous networks to improve network operation and maintenance efficiency. The third category is in the government and the industry field. We are developing various large models for multiple vertical industry to provide AI capability in this sector. X refers to various applications empowered by Nebula LLM. For example, AI coder can assist the developer in programming, and AI smart customer service can help handle network failure complaints, etc. We are convinced that Nebula LLM can be the catalyst for the enterprises in their transition to become truly smart. Next, I will introduce a specific case study showcasing how Nebula LLM had been deployed and utilized in ZTE. First, we need to determine where large model can enhance efficiency within R&D process. The entire R&D process can be broken down into 7 stages, such as planning, requirements, etc. For these stages, we are identified high-value application scenarios marked with red star. Here, we pay a special attention to the code generation scenario, since programming is the core activity in the company. If AI can code faster and with fewer errors than humans, it will extremely improve R&D efficiency. Therefore, we are concentrating on enhancing the code generation capabilities of large language models. We have also established an application platform in our company to support development and application of large models. The comprehensive platform consists of 4 parts. The first part is corpus database, which use to gather, store, manage both public internet data and in-house company data. It offers multi-tenant storage at the petabyte level, accommodating multiple users while maintaining data security. With a Spark cluster comprising over 100 servers to process the massive data. The second part is our AI cloud, used for training and inferencing of large models. It efficiently manages all GPU resources and provides a complete machine learning workflow of training, fine-tuning, evaluation, optimization, deployment, and services. This cloud-native infrastructure ensures our capability to train and deploy large models effectively. The third part is the service proxy, which provides a unified large model API service for downstream application. This proxy grants unified access to both our in-house and third-party external LLMs. It supports account management, authentication, sensitive word filtering, and auditing to align with the company's information security policy. Lastly, we have the Model Hub, which contains various SaaS services related to RnD, such as AI coding assistance, showcased at the ZTE's booth. You can get more detail there. The development of LLM application can be broken down into 6 distinct steps. Step 1, base model. Firstly, it's often preferable to start with an open source models. This model offers a cost-effective way to test and verify concepts. Based on this test result, a decision can be made whether to train an in-house base model replace to open source base model. Step 2, incremental pre-training with professional corpus. We use professional corpus in the R&D field, mainly in technical document and source code. By this step, the model learns more professional knowledge, enabling it to produce a higher quality code and tackle more complex problems. Step 3, supervised fine-tuning. We use supervised fine-tuning training to improve the performance of the model on specific tasks. Let's consider a task to generate a piece of code based on a natural language description. By carefully making tens of thousands of examples for SFT, we can significantly improve the success rate of code generation. Step 4, evolution. We have established a series of tests to evaluate the fine-tuned model accuracy. When the best model has been identified, we subsequently optimize its inference performance. Step 5, optimization and deployment. After the inference performance optimization, the model is deployed to the production environment. Step 6, monitor and feedback. The performance of the model is continuously monitored in real time, and feedback data is also collected. This feedback data is invaluable to subsequent improvement, enabling the model's accuracy is progressively increased. There are several key considerations for choosing an appropriate base model. Firstly, the base model should have strong coding capabilities. The industry often uses human evil as one pass score for assessment. Secondly, the model size shouldn't be too large to avoid high inference cost. Finally, the model should have also have the chat capabilities. According to these principles, we believe that Starcoder and CodeLlama, marked with red stars, should be the most appropriate base model for AI coding. Next, we use our in-house corpus for incremental pre-training. We training our models on 512 NVIDIA A800 GPUs with NVLink and RDMA, and use technologies such as 3D parallelism, zero, and flash attention to improve the training efficiency. Finally, we achieved 55% GPU flops utilization during the training. After pre-training, we evaluate the model's performance and the specific task. If the score cannot reach our expectation, further fine-tuning is mandated based on the task. We have tailored fine-tuning for various tasks, such as code generation, code error correction, code refactoring, and unit test generation. For this task, we have prepared more than 100,000 fine-tuning samples. We tried many fine-tuning algorithms and finally found that LoRa and fully supervised fine-tuning, SFT, to be the most effective. The LoRa algorithm, being resource efficient, is ideal for swift iterations and exploration, while full SFT algorithm is optimal for attaining the best performance of the model. The quality of fine-tuning dataset is very important. We have found that the complexity, diversity, and the consistency of the model are very important in fine-tuning. For instance, if a sample is overly simplistic, it doesn't challenge the model enough to tackle hard problems. Conversely, an ideal sample exhibits adequate complexity while also having a clear and constant output format. Such samples are effective in guiding the model towards the desired outcome. To evaluate the model's performance in real-world application, we take a dual approach. For this purpose, we not only select a array of public test data, but also have established our own test data to evaluate the models. The in-house data come from actual R&D projects and can evaluate the model more precisely in real-world scenarios. We are utilizing this dataset to evaluate both public models and our self-developed models, giving us deeper insights into their advantages and disadvantages. As an outcome of our effort, we proudly present BebulaCoder. We have released 3 versions of this model in our company. The most recent, version 3, built upon the CodeLlama base model. We use 300 billion tokens to incremental pre-training, while requires 20 days on 500 GPU. The subsequent fine-tuning phase, which based on 32,000 samples, take 2 days on 4 GPU. As a result of this enhancement, the human evil score of the model witnessed a significant jump, moving from 48% to 75%. To the best of our knowledge, this is currently the highest score except GPT-4. Developing LLM applications require massive GPU resources. An LLM with 15 billion parameters require more than 40 GB memory and only deliver a throughput of 30 tokens per second. To serve our company's 30,000 R&D engineers, we would need thousands of GPUs. Recognize this challenge, we have done many optimizations to decrease source consumption, enhance throughput, and minimize latency. All of our optimization focus on 3 layers of our LLM server engine. We introduce contextual bunching at service layer, KV cache, page attention, 3D parallelism in engine layer, and layer fusion, flash attention, and interval quantization in operator layer. This works largely improve the inference performance of our LLMs. The throughput of a single GPU has increased from 13 tokens per second to more than 1,500 tokens per second, almost 50 times increased. A single 40 gigabyte A800 GPU can support more than 250 users, substantially reducing the development cost of the AI coding application. However, we noticed that there is a downside. As the context length increased, system performance degraded rapidly. Addressing this challenge remains an essential task for our future endeavors. In conclusion, I sincerely invite you to visit our booths. We have prepared a video demonstration showcasing our LLM applications. I believe the detailed information may be of your